first time you called me late. Loved you for your wits and your wicked games. Yeah, always on my mind, always in my brain. Yeah, with you the summer came and went in a day, and I've been craving you since the first time that I sat by your side. And I've been on my knees thinking time is gonna fix me inside. No, nothing's gonna make me forget, and I don't think I want to forget anyway, yeah. No, nothing's gonna make me forget, yeah, I don't think I want to forget anyway, yeah. I can feel you near when you're miles away, yeah. You can make it shine when the whole world rains. Always on my mind, always in my brain. With you the days are long and the nights are late, and I've been craving you since the first time that I sat by your side. Ooh, and I've been on my knees thinking time is gonna fix me inside.
Okay, we're just kicking the tires here, and we're going to get into it. Just making sure we got audio. We are live streaming on Twitch and YouTube tonight. So, Twitch, we are on twitch.tv/IQ Workshop, and if we're on YouTube, it's youtube.com/IQ Workshop. Funny thing that. Tonight, we're going to be working on the LumenPnP. We got a bit of an update to give you, and we're going to be looking at doing some work on the firmware. So I think we ought to just get into it, right? Hello and welcome. This is the IQ Workshop, a place that I come to attempt to get smarter. Right now, I am working on getting ready for a circuit board. Do I want to say it's a commission? It's not a commission, it's a collaboration. So I am working with a bunch of creators, and we are building an electronics project. I'm not going to disclose what that electronics project is yet in terms of its functionality, but I will be soon. I will be showing off the internals of the project tonight, and we're going to take a peek at why am I taking so much of my time to build a pick and place machine, specifically the LumenPnP. So we have this project to build, and we have we've achieved some pre-orders, which is awesome, and we've got a bunch of units that we're going to be making, and we're going to then make additional units on top of that in order to sell at an event. These units, we're talking about 100 units, right? So in terms of PCB manufacturing, that's a very low number, especially when you think of, I don't know, a mobile phone, for example. You see these things manufactured in their thousands, tens of thousands, if not more. And essentially, we're doing a very guerrilla hackerspace type, almost like a Kickstarter per se. But as I say, we're doing this ourselves. I built the first 4 prototypes. Those prototypes with a soldering iron took me 4 hours to assemble by hand. We have gone to surface mount components, and I did a very unorganized construction of one of these boards. One of these sort of hardware shakedown boards. Yeah. What is the test article? Yeah, it was a test article, and essentially we put this together again with a soldering. No, this was the reflow oven, but we pasted the board. We were using 0805 components on 0603 pads, so we were kind of shoehorning things into places that they really shouldn't have gone. And that was in with the guys of the 0603 components were in flight. They were being shipped, but we needed to validate the hardware. And that board took me approximately 2 hours to assemble. Now, 100 boards at 2 hours is less than ideal. So what I then did, I actually got a bunch of 3D printed bins, and I wrote on them the components, right? And I dispensed the correct number of components for the board. And then I timed an organized assembly of the board. And we're looking at approximately 23 minutes per board in order to, place these components, right? So this is going to be the most inefficient sort of process. It's not refined. I actually put together a little manual of how to put the components out. In fact, let me show you that folder. So this is my assembly file. This is my assembly log. We're likely to see the Lumen here, are we? Yes, there's the Lumen. We're going to be looking at you in a minute. Right, so here's my assembly folder. And in here, I have a list of all my individual components. And then each page is a representation of the board. And I've grouped them into sections, right? So the first one is transistors or transistor type components. So we're looking at N-channel MOSFETs, P-channel MOSFETs, and transistors. And we've got the map. Essentially, all I did was to take the board outline from my EDA software, and I tiled it, and then I printed it out. And then with a highlighter, I highlight where each of the components go, right? So I can literally have the board in front of me and say, right, the N-channel MOSFET, of which is only one, needs to go here. So I can pick the component, follow the map, and place them on the board. Next up, we have the fuses. And it tells me where my fuses go. Then the resistor map, and then there's like various different components ranging from 1 ohm all the way to 100k ohm. Then my capacitors, and we go through each of the components. It's the same design of the board. It's just telling me where each of these components go. And this is in the guise of trying to get into a rhythm, right? I can just unplug my brain. What does this page tell me I need to put? It tells me I need to put an inductor on the board. So I pick the inductor up and I place it where it's highlighted. Rinse and repeat until such time as I get to the final page, which is the ICs. And I put my microcontrollers and all the chips down. And then we come to a fully completed board. That board took me 23 minutes to assemble from the original 4 hours, that is a significant saving of time. But that is still, you know, when you're building 100 of these things, that's still quite a long time. So here is the assembled board. And I am pretty impressed. This is a little jig that I put together, and it comes in 2 halves. The first half is obviously a little insert with some pins so that I can place the component in like that. And then I can pop this up on top, paste the board with solder paste, and then I can set to putting the components down on the board, and I can rotate it. I don't have to touch the circuit board at all. I can place my components, and that is then ready for the reflow oven. So let me just check we're good to go here in terms of we're not having a technical difficulty. Because I know we're live. I saw we're live, but we have no chatting. I don't know if my chat has broken. If you are in chat, why not say hi? There we go. There we go. Cool, cool, cool. Just needed to make sure that everything is working as I would hope. So that's good. All right. We'll keep going. We'll keep going. Right. So what does this mean? Well, it means when we are trying to assemble like 100 boards, that's going to take quite a bit of time. How much time, you ask? Well, the panels, the boards come in panels. And here is one of the said panels. There are 14 circuit boards all in panel. So to put this together with no breaks, we're looking at approximately 5.5 hours of assembly time. What this is, 5.5 hours doesn't sound too bad. But what I'm concerned about is human error, because, over time, you're going to get tired. And, I could end up placing a component in the wrong place. If I can get the Lumen up and running, the Lumen will place the components consistently on the board. Yes, it'll still need inspection, but there's a lot of time saving, right? Still to be had on the table. I'm hoping that I can get these things down, more again, right? So 23 minutes per board, 5 hours per panel. That's 5 hours worth of work for assembly just on this. So that is what I'm working with. So, right. Where are we at with the Lumen? Well, I kind of teased it a little bit earlier, but here is the Lumen. Let me see if I can square you up a little bit. You're a little bit wonky. Get in there. There we go. Right, so the Lumen has the first stage plate fixed as a reference. I have to take this back off and give it a sand. These have been sanded to predominantly deburr them and possibly prep them for any form of painting that I might want to do. So yeah, I'll be sanding this plate. So I'll keep this in place, fix plates number 2 and 3, and then I can remove plate 1 and do the work on it. We have the Z-axis fully assembled, minus the pick and place motors. So the pick and place motors are a set of NEMA 11 hollow axes motors. and it has a CP40. It has a CP40 attachment on the bottom, which allows us to remove, he says, remove the nozzles. So we actually have a tool change option where we can swap out the nozzles for different sizes to pick up bigger or smaller components. This motor sits in this housing like so, and it is used to rotate the component. So it'll pick the component up from a feeder of some kind. It'll bring it over to this receptacle here, where there will be a camera fitted. It'll hover it over there. It'll figure out which way round the component is using a vision system. And then it will rotate the motor to orientate the component before taking it off to its designated location and placing it. So these motors have still to go on. And these motors, you'll notice, have got this adapter on the top. This is a pneumatic fitting where we'll be feeding in a pipe into here that draws the vacuum. Right, so we have a vacuum pump. It's going to pull a vacuum on this motor in order to suck up the component to the tip. It's going to hold it and take it over to its place, drop it, and then we release the vacuum, move away, and the component is then down on the circuit board in the paste. So the Z-axis is complete with its linear bearings. NEMA 17 motor, limit switch for homing. I've made a modification to my Lumen from the original V3 design. I have added a drag chain on both the X and the Y axes. The motors are fully wired on all axes. And we have, let me just drag this over here, right? We have Frank's brains. We found Frank's brains. Last time we were working on a ramps board that had quite a bit of corrosion damage because of its environment. It got moist and it corroded. But Frank's original brains were kept in a sealed box and is in good nick. Can you tell I've been busy? Look at the state of this workshop. It's crazy, man. I got to tidy up so bad. What do we got? We've got a custom bracket, which I need to swap out because it's a little bit flimsy. I see that the next version of the Lumen does come with a drag chain arrangement instead of like the snorkel drag chain that it had, that was originally designed to come off this mount here. And it kind of hooked around, and the X motor kind of like fed in. It was like, it was a work in progress. I totally get that, but the XY drag chain is a much better arrangement. So my Y-axis drag chain bracket I'm pretty happy with. I might put a knockout here so that route the cables down and under the machine this way. That's absolutely a possibility. But we'll wait and see how we get on. This one definitely needs a redesign. I'm probably going to take it off, put some braces in it, and also knock through a hole here to go through the X-axis brace and actually screw this down. But for now, this is operational. This will work, right? Homing on these limit switches is very coarse anyway. We'll be homing using an optical system. There's going to be a datum which goes here, and it has a target on the official Lumen. They use a circuit board which has fiducials that we essentially look for using the camera, and then the machine knows where it is in 3D space in the machine. Now, I'm making my own datum. I've got a knockout here, which I've 3D printed. I'll be sanding this nice and flush, and then I'm going to laser engrave it. And then I'm going to come through with probably some acrylic paint to give it a contrast color, probably black. And then I'll have my own datum using the laser cutter. all the plates have, like I say, all the plates are in and have been machined using my CNC. And we're good to go, right? We've got to power up this ramps board. We've got to get these axes moving. Now, I've already done some work. We've got it homing, which I'll demonstrate, but it's not perfect. So tonight, we're going to be working on modifying the Marlin firmware further in order to do a couple of things. The most important thing is that we get the X, the Y, and the Z axes calibrated so that when we tell it to move a set value, it actually moves that set value. That sounds pretty obvious, right? But the machine, these stepper motors are pretty dumb. They just do what they're told. Now, depending on your gear ratio between the pulley and the belt and whatever else it's driving, when you command it to go 100 millimeters, it may go 120, right? That's no good when we're placing components as small as 0603. So especially over the width of this bed, that would be horrific. Components would never go down in the places that they were supposed to go in. So we have to get that calibrated. That's the first thing. The second thing is we have to get the machine boundaries set correctly so that the firmware in Frank's brain knows how wide this machine is and how deep the machine is, and also how high we're going to be moving the tool heads. So, like I say, I've modified the firmware already to get some of the motion working. Additional things that I need to get working will be the auxiliary ports so that I can turn pumps on, turn lights on, and do all the things that the PNP needs to do. So let's hook it up to the PC, and we're gonna command it a little bit, and we're gonna see what happens. So I'm just gonna plug into USB right now. Okay, I just heard that connect, and I need to plug in my power source if I can find my cables. Nice. Okay. So Frank lives. Genius, thank you so much. Appreciate the comment. So just for the history of those of you who are unfamiliar, a lot of the parts that I'm using in this LumenPnP build, they come from the first 3D printer that I ever built from scratch, and I named that printer Frank. So Frank is being reborn. It's going to be resurrected into an electronics pick-and-place machine. Frank was going to be a better spec 3D printer, but it was not to be. Fate did not have that in Frank's future. So Frank is back. Oh, thank you so much. I hope you're subscribing and hitting that thumbs up. Thank you, genius. Okay, so I am just going to hook up my a terminal. Let's open up the terminal to the printer, and we get connected to the printer. And we're just going to drive this with basic G-code commands. So what we're going to do, I'm going to send a G28 command, which for those of you who are, I'm glad you're already subscribing. If you have any questions about this project, please feel free to ask away. So we're going to issue a G28 command. The G28 command is a home command. So what we're expecting to see is the X-axis come over to the limit switch here. This carriage is then going to come towards us to this limit switch mounted on this post here. and then we should see the Z-axis home. So G28. G. Yeah, G28. Hit return in 3, 2, 1, go. Oh, it's not going to do anything. Do you know why? Because I haven't turned the power supply on. We're having power through the USB to the microcontroller, so it is doing what it thinks it's supposed to be doing. I'm just waiting for it to error out so it stops trying to move. There we go. I'm going to hit the reset button, like so. Now I'm turning the mains voltage on. Right, here we go. Let's do that G28 command again. And then we should see the machine move, hopefully, if I've done everything right. Here goes nothing. 3, 2, 1, go. All right, so there goes the x-axis. Okay, and here comes the Y. You'll notice that the machine was in the center. And the reason that the machine was at its physical center was because if you don't know which way the motors are going to take off, then you want a bit of tolerance either way. Okay, it's errored because it's outside its limits. So I'm going to hit the reset button again. And then we're going to G28 again. Go. You should see the x-axis just jiggle. There we go. And now it's going to home the z-axis. There we go. It's reached its home point. So that is less than ideal. One of the things that I'm making to assist in the manufacture of the circuit boards, there is somewhere in the region of 30 separate components on this board. And that's going to be pretty difficult to manage. So I am making a bunch of feeders. So these feeders, they take a reel of components. Let me grab a reel. Let me show you. Rather than tell you, I can show you. So we get a reel of discrete components. In this case, we are looking at a reel of capacitors, I believe. Yeah. So what have we got on this reel? So we've got 100 nanofarad. We've got 100 nanofarad reel of capacitors on this reel. What's the quantity here? There's 4,000. There's 4,000 capacitors on here. So what happens is this fits on here like so. The tape unwinds and goes through this feeder. The film gets peeled back and goes through this gear mechanism. And this large red gear, it's got a series of like these little pins which match up with the pins that are in this tape. So as the tape gets pulled through, we're going to actually set up a job so that the nozzle of the pick and place machine pokes its nose through the perforations in the tape, advances the tape, and in doing so, it causes this gear mechanism to do this, right? So the plastic film that stops all the components falling out feeds up through this mechanism and gets spat out the backside. So there's always components in this little window that the pick and place machine can actually grab and be ready to place onto the circuit board. Now, why is that a problem? Well, the problem that we've got is that these reels, they mount, as he drops the reel, taut like a cat. Right, if I put that here, you can see that that's going to crash. The machine is going to crash into the reel. And we don't want that. So we've got to figure out how are we going to stop this machine from going from this corner, the 0 point of X and Y, off into the distance and ripping all of my feeders off the rail. I already know the answer to this question, so we're going to go in and we're going to fix it. And while we do that, I'll answer some of the questions that are popping up in chat. So the firmware called me to enable a probe for Z homing, which we disabled, but there's one thing that we didn't disable. All right, so I'll show you what we're talking about. So let's switch over to here. This is the code view. I'm going to zoom in. Can I zoom in? View. Appearance. Can I zoom in? Control plus equals. All right, control plus equals. Okay, it's a little bit bigger. Hopefully you guys can read that. I'll keep this indent here so I don't get in the way of the code. Let's close the terminal window for a moment, and we're just showing the code itself. Right, let's quickly look at the questions. Trying to dive deeper into G-code programming, it seems... Right, okay. So G-code programming you can do in a text editor. When I was in college, a long time ago, we're looking at the early 90s. I did a course for manufacturing. I was headed going to heavy industry before that died in my local area. One of the things that I did do was G-code programming, and it was very basic, but it was a case of we had to mill or design a program to mill a square in a piece of material. Very basic, but over time it got more complicated. So we would have to program it to move to X to Y, and we had to program radiuses in. I couldn't tell you, right, what the code would have looked like, because, you know, we're talking a long time ago now, right? But very much these days, G-code is done via CAD CAM software. So you have a CAD program like Fusion 360, like Atom 3D, and you design a 3D model. You then use a CAM software. Libre do a CAM product. Fusion 360 has the CAM built in, but you design your tool, you do your setup, and then you do the post-processing, and the software generates the G-code. So, yes, the capacitors are all the same. They're used for a production line. So that's exactly what we're setting up here, Genius. We're setting up a production line. We're going to be manufacturing... these circuit boards that we've designed. We've got 100 of these to make, and I don't have much time to make them. And ideally, I don't want to be making them by hand. I will if I have to, but I don't want to. So we're building the LumenPnP to do the heavy lifting in that regard. So let's go back to the code. Right, so let's go in. So we've got the firmware, the Marlin firmware. This is Marlin 2.0.9.7. I think that's the latest revision of the firmware that the RAMPS 1.4 Arduino Mega combination can handle. So we're using Visual Studio Code with Platform IO, and we're going to go into the code and we're going to make adjustments to it so that it doesn't do that homing thing. Yep, there are, but we're doing this all in-house. We might move to have this board being manufactured, but the cost at the moment means it's beneficial for us to make this ourselves. And I showed this on stream a little earlier. I'll show it again. So here are the circuit boards. They come in a panel, and it helps if I turn off that camera. All right, so they come in a panel. The panel has 14 boards on them, and the machine is going to place all of the components down, and then they get placed into my reflow oven, which is just here, and they get soldered. So, you know, this is guerrilla style hackerspace startup, and I decided that I'm not. Ideally, I don't want to be putting these things down by hand. I'm going to be doing a pick and place, right? So these, I believe, are from JLC. My partners in crime ordered the boards and had them sent to me. So anyway, let's get into firmware hacking. So the setting that we need to disable is this safe homing. When we're dealing with 3D printers, typically they don't want to crash any sort of physical Z probe. So what happens is it usually goes to its midpoint and then homes at the center of the build plate. So it's nice and free and clear of any obstructions. We don't need to do that. In fact, in our case, that's counterintuitive because we're going to crash all of our feeders. So we're going to disable this feature by just commenting out this Z safe homing line just here that I just highlighted. So let's go ahead and do that. We're going to upload the code and see whether or not that has had the desired effect. Yeah, I mean, the boards are professionally made. We might go for a PCB assembly or PCBA service in the future. The volumes that we're looking at the moment do not warrant the outlay for a PCBA service. This is going into a commercial product. This product is being sold. So I will post more information about the product when it's appropriate, about what it is, and if people are interested, where they can go for pre-order. But right now we're hyper-focusing in on the manufacturing side of it. We've got a limited time to deliver the first batch of pre-orders. I've got about a month to get these units made, which sounds a long time, but when there's a day job to consider, when there is home life to consider, there's the unexpected to consider, a month goes away pretty quick. So we need to haul some butt, and we need this this project to get off the ground and start working for us. So, and it makes good content, right? Making a machine from scratch. This is so for anybody who's interested, we are making the LumenPnP from Opulo. Opulo is an open source company. It has made the designs for the LumenPnP freely available. There is a GitHub repository for the machine itself. And all I've done is download the GitHub repository. I have 3D printed all of the frame connectors. I've ordered 2020 extrusion, and I put this thing together, right? It's pretty cool. It is pretty cool. Right, so we're uploading the firmware. The firmware's just been built. We're just waiting for the upload to take place. We should see that happening anytime. Here we go. Here comes the upload. So we're writing the firmware now. Yeah, genius. I'm always open to working with people. I would love to get a channel sponsor that would enable me to get a lot of this content out faster. I've got my home automation low voltage switch, 4-channel switch to get out there. Okay, so we're done. We've just changed that setting. We've uploaded the code, and now we want to find out, has it had the desired effect? So let's go and have a look at the Lumen. We're going to give it a G28 command. And here's what I'm expecting. I'm expecting it to home here in X, home to Y, and then Z should home right here. It shouldn't go over there. It should come here. Let's see if it does that. So G28. Here it goes. Okay. It's coming towards us. Awesome. Awesome. Right, okay. So that's the first thing we needed to do. Now we need to figure out how to get these two brackets in equilibrium. So ideally, we should be going to a 0 point. So let's come and find the code. And we're looking for the homing positions. We got the feed rate. Let me just write this down because we might want to adjust the homing feed rate speeds. At the moment, it's going at 30 millimeters per minute, which is pretty slow. So what line are we? 1953. 1953 is homing speed. Okay, I just jotting that down on a post-it note so that I can come back to that in a second. Right, so we got to figure out where our home positions are. Let me see if I can just do a find. Okay, park the nozzle at a given XYZ position on idle or G27. Okay, that feature is disabled. I'm just literally this is quite a fully featured piece of software for the firmware. Let me see if I've got. It was a file that we had to modify in order to get this working the way that we wanted it to. So give me 1 second. Looking for a GitHub repository that gives me. Here we go. So this is the openpnp. openpnp is going to be the software that we use to control the Lumen. And this is openpnp's suggested modifications to the ramps, the Marlin firmware for ramps. So what I'm looking for in here is one of the options. Okay, we're going to have to come back to steps per unit. We're going to have to adjust that. Or steps per millimeter. Because that's where we're going to go next after we've done this next bit. Here we go. What's this? So this is probe offset. No, that's not what we want. Probe speed slow. Clearance deploy. Bed size. We're going to have to fix that after we fix the steps per millimeter. Okay. Define minimum position 20, max position 20. So that's the extremities of how high and low that the z-axis will go. Minus 20 will be one nozzle down. Plus 20 will be the other nozzle down. And then 0, these should be in equilibrium, right? So... I gotta find the G code for this, I think. Okay, so let's have a look at the G code. Oh. M114, right, is going to get us the current position. So let's come back here. Let's open up a terminal, and we're going to send M114. Oh, we've got to wait for the terminal to connect to the printer or to the machine. Okay, there it is. Okay, so X coordinates is 0, Y coordinates is 0, Z coordinates is minus 20. Right, so it's homed at minus 20. So we got to figure out how we tell it to go to 0 after homing. And I'm not quite sure how. Okay, looking at a forum post here. How to set Marlin XY after homing. The reason of protecting my flex. Right, set the define Z clearance deploy probe 10. Even though you do not deploy the probe define clearance between probes 5. Okay, so we want to define Z clearance. So let's see if we can find that. Yes, it homes at minus 20. So let me just show you what I'm talking about. If I send a G28 command, you watch just there, right? Okay, that's minus 20. Right? If I say G0, Z0, to send it to a 0 point, it goes there. Okay? So we can do that, but I want this to do it automatically at home, right? So we're going to find... Okay, there it is. There's ZR sets. Carefully set Z deploy probe clearance between the closing for probing. Tune and adjust. -2. So if I say 0 here. Oh, hang on. It says -2, right? Carefully set Z clearance deploy probe and Z clearance between to avoid collision during probing. Tune and adjust. Okay, so examples. So that's the offset. Probe margin. Most probes should stay away from the edge of the bed, not the probe. Right, okay. Probe feed rate. Feed rate slow. Okay, let's see if we can. It's a second. Ah, right. Clearance 0. Right. So if we say 20, let's upload the firmware and see what that does. I'm hoping because we're at minus 20, it'll probe. It will go back to 0, right? That's what I'm hoping. So let me write this down in case we go off somewhere. Line 1455. 1455 is Z clearance. All right. Okay, let's get this uploaded. I want this to be defined in firmware. I don't want this to be defined. I don't want this to be defined using G-code commands. Yeah, the most logical things don't always work, though. So while we're waiting for that to upload, let's quickly talk about what's coming next. So the next thing I need to do is to program some, find the pinouts for some of the auxiliary ports, because we have a bunch of things that we need to drive. What do we need to drive? Well, we need to drive 2 vacuum pumps. These vacuum pumps are what are used to suck the component out of the tape onto the end, and they get held as the machine moves and places it, right? So that's that. We got to drive that. We also have to drive a solenoid. Now, this solenoid enables us to release the vacuum. And in conjunction with these two, we should be able to do like a push-pull, close the vacuum out, and place the parts, you know. But we need to drive these independently, right? So we need this running. And then when we've placed the part, we need this to stop, and then we need to run this so that it releases the component. It's complicated, right? So we've got to like do the pinouts of those. We've also got to hook up our vision system. So we've got a bunch of cameras. This is the camera looking down. This is on the Z head. It looks down at the board. It's used to home the machine optically. It's also going to find the fiducials that exist on our circuit board. And we will then be able to place our components using that, right? Then there is a second camera, and this camera looked up. This is the one that I was talking about that goes into the receptacle, right? Just here. That's going to go there looking up. And what the machine does is it picks the components up. It picks the components up and it shows the camera that component. And it uses a vision system to say, okay, what is the orientation of the component based upon where it's going to be placed? And it then rotates the motor so it aligns the component with the pads that it's going to land on. And then the machine takes it over to its location, drops it, job's a good one. That's the theory. But we've got to make this work, right? So there's a ton of things that need to happen. I don't know if I actually uploaded the code there. It says success, but I don't know if that was from the previous attempt. So we're just going to try it again and just make sure that we are at the correct point. So what I'm expecting this time, yeah, picture recognition, correct. So the vision system can see what's going on, and it makes it a very so homing with the micro switches for components which are like, I mean, we're working with components like the smallest components I've ever worked with. So we've actually got a max IC on here for a fuel gauge. Oh, I can't get the microscope working because we've stolen its power supply. But if I just do this, at my fingertip is the max IC, and it is one of the smallest components that I have soldered. It is tiny. It's about 3 millimeters square, and there are 8 pins on it. Oi, oi, frog! Welcome in, buddy. How are you doing over there on Twitch? So we're firmware hacking tonight. We've already fixed one problem. We're waiting for the code to just compile, go up, and hopefully we fix the next problem. I'm hoping. We don't know yet. Now this is going to be the next bit. The next bit's going to be a bit time consuming because we're going to be calibrating the X and the Y axes so that the steps that we tell the motor to move translate into the same dimensions in the real world. So we're going to go quite coarse, and then we're going to refine it. Okay. Oi, Frog, have you seen the Lumen? I don't know if you have, but we've got a machine that's moving. So there we go. The loop, it's built, it's uploaded. We should be connecting to it. Right, we're connected. Oh, no worries, no worries. So Oi Frog says he saw the machine earlier. He's been lurking a while. So if you're watching on YouTube and you see me responding to somebody that's not chatting in the YouTube chat, that's because they're over on Twitch. We're live streaming on Twitch and YouTube. And vice versa. If you're watching on Twitch and you see me talking to somebody, I'm talking to somebody on YouTube. Okay, let's have a look to see. Has it played Doom? Not yet. Not yet. Baby steps. Baby steps. Right, okay. So we're going to send a G28 command. What I'm hoping for is that these brackets rest in this position when we finish. If one's higher than the other, like by a big margin, like this, that's not what we're shooting for. We want these to be... Aha! I hear you, Oi Frog. I hear you. The struggle is real, man. Right, G28. G28. Here we go. So we're going to home X, then Y, then Z. There goes X. Come on. Come on. Come on. No! Ooh. I didn't do it. The forum post lied. Okay, let's see what else we've got going on in this forum post. We could try -20. We could try -20. Let's see what that does. I mean, we are iterating a little bit. So while that's building, just want to make sure. There we go. It is building. Okay. So this is 3D printing, right? But it's the same thing. Z-axis offset. Uh, 1453 we got. Oh. We could try changing these values here, right? Probe offset range minimum. We could say that it is like 0 here, maybe. Let's see what this does first, though. Let's see what other examples of offset that we've got. So these aren't enabled. Hot end offset XYZ. So we're looking at a firmware, right, that deals with a bunch of different boards and a bunch of different hardware and a bunch of different Cartesian sort of or motion systems, right? From a standard XYZ Cartesian system to Delta printers to Core XY. This firmware does quite a lot. So it's about finding the correct values. Just take care that we mean the same axis you had, +20 Y or Z. It was Z. Yeah, this is all the Z axis. Okay, it's compiling right now. And we made an adjustment on line 1453. Oh, actually, no, 55, sorry. Clearance deploy probe, clearance for deploy stow. Okay, we're about to upload. Genius, I'm not quite sure of the question. I've lost a little context there, apologies. Okay, so we're building the firmware. And we're going to upload it. And we're going to see. We're going to see what this does. Now, why did you change? There's ghosts in my system. That's the problem with chat delay, unfortunately. Okay, there we go. So we've uploaded the firmware. Let's go ahead and have a look at the machine and see what happens now when we're home. So we're going to issue another G28 command. Let's see what we get. So homes, Okay, it still doesn't go to the correct location, right? So that clearance, I don't think it makes much of a difference right now. So we're going to set it to 0. How else can we do this? Otherwise, press stop. No, I mean, I can make it stop where I want it to stop. Yeah, sure. But that's not what we're after. We need this. We need the firmware to know where we want this thing, right? I think it was an M114 command, if I'm not mistaken. It's not magic. No, it's not magic. M114. Okay, so Z is definitely at -20. Yeah, right? Yeah, I got a stop button. It's not going to work for us, though. It needs to be correct. Oh! Did anyone just notice define Z after probing? What do we reckon? Do you reckon that could be it? So if we turn around and say define Z after probing and tell it that we want it at 0, I wonder. Oh. Let's see if that's what we want. Probe low point, 1460. So I'm making handwritten notes here about what we're changing, because there's a good chance that we may need to come back and undo some of this. Where were we? It wasn't 1460. 1458. 1458. Z. I potentially need to clean up the code when we get this working. If we change a bunch of values that we don't need to, you might need to set them back to what they were before. So if we can't get this right in a second, in the next few goes, we might park this particular piece and we'll move on to steps per millimeter and getting the bed size defined. I think that's probably what we're going to do, right? Okay, so code is scrolling. Keep scrolling. No problem. No problem, genius. Look away. Right, so we're getting this loaded up. It's about to flash. There we go, it's flashing. So my hope is that by this weekend, we have a LumenPnP that is potentially in an operational state. That's going to be the stretch target. Alrighty. Okay, waiting for us to connect. You had to put a pager on charge, Oi Frog? Oh my word, that is a retro problem. Right, okay, G28, come on. Show me the money. Here we go. X, Y, Z. Come on. Ah! That's pretty cool. You've got a pager connected to the ham radio network, so it still works. That's pretty slick. That is pretty slick. Right, so we're going to have to park this, right, for now. And we're going to have to do some work on the steps per millimeter. So I'm going to manually park this at 0. So we can do that by G0, Z0. And then we hit return and we move to what it thinks is the 0 point. It's not quite, but you can even figure out how to use curl to ping it. That's cool. Just don't let that curl get out there, right? Because otherwise you just get stuff sent to it all the time. Not that I would do anything like that. I didn't do that. Anyway, right, so back into the firmware. We're going to be looking for steps, right? Specifically, steps per millimeter. Oh. Let's uncomment that Z after probing. We can cross that out as we did that. Right, control find. Oh. Okay, so default axis steps per unit. 80, 32, 106, 8.8. So this is X, Y, Z. Yeah, X, Y, Z. And then I believe that's extruder 0 and extruder 1. I think. Right, so X, we get that moving pretty sharpish, right? 5, 6, 7, 8. Very good. Very good. I see what you did there, Oi Frog. I see what you did. You should not be proud of that. Okay. Righty ho. So we're gonna go a bit lo-fi. We're gonna go a bit low tech. I'm just gonna turn my print farm off. Ziggy, turn print farm off. All right, cool. So what I'm going to do is I am going to place my tape. What happened? Okay, something's gone a bit screwy with my deck. So I'm going to find a place that I can hook my tape to and figure out the 0 point. And then we're going to send this off. Tell you what we could do. Ha! That would be kind of neat if I can pull this off. I'm going to put a little bit of double-sided tape. I'm going to put some double-sided tape on the lumen. And I'm going to stick the end of my tape to the lumen. Like I say, we're going lo-fi. So, a bit of double-sided tape just here. Tweezers. Tweezers. I'm struggling to grab the paper. Okay, we can wash that off with a bit of isopropyl alcohol a little later. Right, so if I go... That's kind of funny. Oi Frog says, years ago he was abusing his Fitbit by doing lots of walking for a while and was nicknamed Steps at one point. Right, so we're going to home everything. And we're going to say G0, Z0. Right, and now we're going to tape my tape to the machine. If this works, it'll be amazing. If it doesn't, well, oh well. Okay. So now I'm going to issue the command G0 X 100. And we're going to see how far this machine actually moves. So I'm going to hold down here. This could actually work. This is kind of funny. Hold down and like stretching across to hit the return key. Here goes nothing. Okay, that's not bad. It's not perfect, but it's not bad. It's around the 100mm mark. So that tells me the gear ratio from my x-axis along my y-axis is, give or take, correct, right? Which means when I come here, see Waffles, welcome into stream, buddy. I need to change this to 80. And I'm also going to change this to 80. I'm going to set them all to 80. This could be a horrific idea. Right, but we'll see. We're going to upload the firmware. And we're going to see what happens. And as long as we get an approximate value that's in and about the right sort of space. Let's get this tape off this while we're talking. As long as we're in and around the correct value, that'll do for now, right? We'll dial it in a little bit better. We have to have accurate steps per millimeter. But right now, I can't send the machine the full width because it's going to crash. It's going to crash into here, right? Because it's going to travel too far. So that's not good. Equally going that way. So until I get reasonable steps per millimeter, I don't want to change the bed size because it limits me from being able to do some damage to things. Hey, Paul Gibson. Welcome in, welcome in. A frog in two places. That's kind of funny. I read you in stereo. So, yeah. Where are we with the firmware? Okay, so that is compiling. It is on its way up. And this is going to be a little bit of a repetitious iteration here, where we make incremental changes to the firmware, upload them, and see what changes they actually make. If something goes bad, we back out. But what we don't want to do is do something bad to the hardware. So let's see what happens. Okay, the firmware's built. It's now gonna upload it. Okay, it's writing. Okay, M92 tells us we can change the steps per millimeter. So in theory, we could change the steps per millimeter on the fly. And I don't know if we can do I think it's M500 where we can save the values. But I'd rather have them natively in the firmware. Okay, so that's now done. Let's see what a G28 now gives us. Okay, so we are connected. We're doing a G28, which is a home command. Okay, we have changed the Z-axis to 80 steps per millimeter. So let's see what happens when we tell it to go to 0. So bearing in mind, we're looking at this, right? These two little buckets going up and down. So that's definitely not right, but that's fine. If I command this to go 100 millimeters, so we haven't actually changed this value. Now this machine's moving relatively slowly. I think we need to bump that up a little bit, right? I'm going to change the feed rate. So let's go G0 X200 F 25,000 millimeters per minute. That's good. That's very good. Now, I think the bed is defined as being 200 millimeters. Let me just try going to 300 millimeters. So G0 X300. We shouldn't see anything move. Oh. G0 X400. Oh. Okay. Okay. Okay, 400. 400. Twice that speed, or we may fall asleep, right? Absolutely. Right, so if I now say, let's send the y-axis, G0, Y400. Dear God, what's going to happen? Okay. Okay, so we lost steps on the y-axis. We lost steps on the y-axis. So let's do a G28. Let's home, because it's now lost. It doesn't know where it is in space on the y-axis, and it'll crash and do all sorts of skullduggery. So let's go 20,000 instead of 25,000. Let's go 20,000. G0 Z0. Oh, that's not right. So let's go G0 X400 feed rate 20,000. Go. Okay, good. G0 Y400. Okay, we lost steps again. So I can only assume we got one or two things going on here. I'm just going to power down. Good morning. Okay, so my stepper drivers are getting pretty warm. I probably will need at some point to calibrate the stepper driver power ratings. Right now, they're just some arbitrary value from when they were last used. Or they could have got bumped when they were in storage and the potentiometer might have changed. What does that mean? It means that the stepper drivers, when they get to a certain temperature, there's a reduction in the amount of current that it can deliver to a motor. And that can result in the machine losing steps. So I'm either trying to drive it, I could be driving it too fast. It could be that I am overheating the stepper and we're losing power to the motor. In fact, the steppers are cold, so it's not the stepper. In fact, I didn't touch the y-axis. Let me just touch the y-axis. No, they're cold. They're stone cold. So it's not the motor's overheating, because if the motor's overheat, again, we can lose power. So you've got to figure out what's going on here. And I think it's a combination of the power setting and a temperature. Okay. So let's boot that back up. Because we haven't done anything to the movement system, we haven't lost anything we didn't already lose. We'll still do a G28 though, just to home everything. So one of the things I have done with the ramps board is the ramps board has one motor output for X, one motor output for Y, and two motor outputs for Z. And that's for dual NEMA 17 on the Z-axis for like the Prusa i3 style printer. I've actually gone into the firmware, found the pinouts for those motor ports, and I've switched X and Y. So the Y now has two sockets. So we may need, as a result, we may need to increase the current that's delivered because it's now driving to two steppers. So you want to level out those heads to Z0 looks unbalanced. Your stepper motors are on board. So it's going to be the stepper motor. It's going to be the board, the firm. Right, it's both actually. So I have to get the movement system correct so that when the Z-axis is commanded to move 10 millimeters, it moves 10 millimeters. And then I need the firmware to return to its 0 point, not its home point. So I'm going to have to dive into the firmware and find out where that setting is. So let me just set the feed rate. We'll go to the feed rate of 1500. So G0 X 400 feed rate 15000. Yeah, 15,000. And go. Okay, G0 Z0. I don't need to set the feed rate. It'll take it from the last command. G0 Z0. There we go. Now let's send the Y. So G0 Y 400. And we lost it again. I wonder if it's acceleration. It could be acceleration. G28. Let's just home it all again because we've lost. It thinks it's now like Y is at 400. I'm going to give it a diagonal command. So G0 Z0. Okay, so if I go G0 X 400. Whee, 400. Y 400. And hit go in 3. What do we reckon? Do we reckon that'll work? Or do we think we're going to lose steps? What do you think, chat? We're going to find out. I've got a chat delay, so we're going to go for it. Here we go. In 3, 2, 1, go. All right. Okay, so when we use them in both, when we use them, I think it's acceleration. I don't think it's motion. So if I go G0X 400 F 25,000, go. G0X0, back to home. What if I send it to its maximum coordinates now? G0, X 400, Y 400. Go. Okay, we lost the Y axis. So I have a sneaking suspicion the current is insufficient for the acceleration. And as soon as it loses traction on those steps, we lose it. So G28, let's home it again. Okay. So we can reduce the feed rate. Okay, so G0X 15,000 or 10,000. F, oh no, X 400 F 10,000. Okay. G0 X0 go. All right. Now let's see if we can move the Y axis. G0 Y 400. Yeah, I think we are bumping into some acceleration problems. So let me find in the code where the acceleration is set for the Y-axis. And if I turn that down a little bit, we might be able to just tune that problem out. I probably will want to come back to this and set this with a better power rating, because we're driving 2 motors here. So it's possibly what we're bumping into. Default max acceleration. Okay. Let's find that. Control find. Oh. Control find. Default max. Default underscore max underscore acceleration. Okay, 5,000. So if I bump that down to, I don't know, let's go half that. So instead of that, go to 500. So we have a little bit of a ramp on Y, but that's okay because we'll come back. Is it making things yet? Says Road Rally Race. You can only recommend E3D boards for G-code programming. The Duet. Yeah, the Duet, it's quite a well-established board. And it's got a ton of features that a lot of boards don't have. I believe it has CAN bus communications. So you have 4 wires, VCC, ground, data positive, data negative, and you can pretty much daisy chain your components along the CAN bus, and almost getting to a point where you can have infinite numbers of devices on there for expandability, which is pretty cool. I do like that. The whole point of this build is, I mean, let's be straight about this. There are easier ways to obtain a LumenPnP. The easiest way is to buy one from Opulo at $2,000. We're not doing that. We're trying to do this as a budget build. So we're making the components ourselves, 3D printing frame parts. We are using parts from Frank, my first 3D printer. So there's a sentimental value in having Frank as part of the assembly line. And it comes full circle in my maker journey, right? Just buy 5 of them. Road Rally Race, I wish I could. I wish I could. But arguably there is a lead time for them, and I need this now. The job has to be delivered on a deadline, and that deadline is about a month away. I've got about a week to a week and a half to get the Lumen up and running. And once, you know, if I can't do it in that time, I will have to reside myself to hand assembly. That's not where I want to be, because a panel is going to take me 5.5 hours to put together, which is the reason we are building the Lumen. So we shall see. We've got work, you know, we've got work for it, that's for sure. And what we're working on right now, the steps per millimeter and the motion system, is one of the most critical components of the overall build. Because if your motion system isn't reliable and repeatable, and it loses steps when it moves from place to place, it's going to be putting components in the wrong locations. So we can't have that. It's got to be right. It's got to be right. No ifs, no buts, no maybes. It's got to be right. Okay, so we've built the firmware, we've updated it. Let's see where we're at with moving the machine now at the speeds that I want to. So let's go to a G28, a home it. PnP farm next to the print farm. Well, you listen, wherever the work takes me, right? This is a collaboration, but this could, you know, this could be the thin end of the wedge. You never know where this is going to go. Right, so let's move the x-axis. G0, X, 400, and we'll go for a feed rate of 25,000. Now we know the X motor can handle this. All right, so we'll hit that. Off it goes, which is why I think this is a stepper driver power issue. So we're running NEMA 17s at 12 volts. The LumenPnP is actually NEMA 17s at 24. So make of that what you will. Right, so if we do a G0, Z0, and now we go G0, X200. All right, so here we go. We're going to send the y-axis 100 millimeters. Let's see where it goes. G0, Y, 100. And we lost steps. You son of a gun. Okay. So let's go G0, Y200 with a feed rate of 20,000. And we lost steps. G0, Y300, feed rate of 15,000. Ooh, we're on the cusp of it there. So let's go G0, Y400, F 12,000. Okay, I think 12,000 is our Goldilocks zone. G0, Y200. Okay, G28. All right, we might be hitting something here. This is quite important for us to get right, because this could be an operational setting. I'm going to look to see whether this feed rate is where I want it to be, right? So we go G0, Z0. Now let's send it. G0, Y400, go. Yeah. That's running pretty slick now. That's not dropping steps. I mean, it could be a bit snappier. But I mean, I can live with this. I can live with this. So G0, X0, Y400. I should use Pronterface, really. It'd be a bit of a graphical sort of dial in. Right, okay. So we're up against our end stop. I can see we're touching this plate here. I'm going to move the x-axis 400 millimeters, and we're going to see how close it is to 400 millimeters. So G0, X400, go. Okay, so we're going to measure from the face of this plate here to there, and we're going to see how many millimeters we've actually moved. Is it 400 or is it? It is 400. So we look to be spot on in terms of our x-axis calibration. Yeah, I'll take that for now. I mean, we may need to tweak it again in the future, but right now I've got to get a reference point for my y-axis. I'm looking for a datum point that I can use. Okay, the thickness of the tape goes in there, so we can probably measure it from here to this post. And there's a adjustment I can make for that. Right, so let's go for it. Woodcraft! Welsh not found. Welcome in, buddy. How you doing? G0, Y400, go. Frank, the LumenPnP, is coming alive. I'm struggling to find a datum point. I think what I might do, in fact, that's exactly what I'm going to do. I'm going to bring this back to 0. G0, Y0. And what I'm going to do Well, we're kind of up in the air about that at the moment. We are definitely looking at going for at least 1 day. The question becomes is, can we make it 2? And this build is playing a part in the decision making. Okay, I think I've marked the linear bearing where this is at. Let me just make sure my 0 mark is correct. G0, Y0. Yeah, that sounds like a plan. If I can make it 2, I will. But, I mean, it's crunch time on this project, right? I've got a deadline to get these out. I've got roughly a month before I'm in the brown sticky stuff. And I'm making these boards by hand. G0Y 400. I'm going to do a cardinal sin here. I'm going to power down my system. So that loses all the power to the stepper drivers. And I'm going to push the axis back to reveal my 2 marks. And I'm going to measure between these 2 marks to see where we're at in terms of steps per millimeter. Okay, we're possibly a millimeter out. Over 400 millimeters. So I think that's going to be good enough. I think it's going to be good enough for our first bake of this. Let me just push this all the way back. Ah, that's interesting. That's something I'm going to have to fix. My drag chain is catching. What is my axes here? We're saying that it's 485 in the Y. 485. Y. 485. Can you hand chase a 0.3 mic PCB tracks? What are you worried about? Well, I'll show you what I'm worried about. I'll show you the board that we're currently working on. And in the x-axis, we're running what appears to be 435, 437. 437. 437. Okay, so I need to change the bed dimensions and then upload the firmware. And then once I've done that, I'll show you the boards that we're going to be working on. And then we can explain why we're building this LumenPnP in the first place. Let me find the bed dimensions in this update. Find bed. It's 12 of 20, right? So where is it? Define bed size. Trying bed. Oh. In my code, please. Find bed underscore. Okay, it's not found in there. So is it in my advanced file? Find bed underscore. It must be in here. And the question is whether or not they've changed the syntax. Super King! When am I making GPUs with it? Oh my God. X bed size 400. Right, okay, so what do we say? We're saying that we are in the X 437. In the Y, we are 485. All right, let's upload this. That's on its way to the microcontroller right now. And then we should be able to move it to its actual maximums. There's a chance that we're going to hit and crash if our steps per millimeter are slightly out. We're going to find that out. Right, so the LumenPnP, why do I need it? So, and it is a need. It's not a want. I'm collaborating with some creators to make an electronics project, which I'm not able to tell you what it does yet, but I will. The time is not currently right, but I've had agreement from all parties involved that I can talk about the board, but I just can't tell you what it does, and I can't give you the pre-order links and stuff like that, all right? But that's coming. That is coming. So this board is something that I've designed, and it looks a little like this. I have 3 versions of this. The CNC nose picker. There's a gap in the market. Says Woodcraft by Owen on Twitch. That's it does do a thing. It does do a thing, right? So this is the board that I've designed, and essentially there are around about 32 different components on here. Not all of them will be used. There's 2 operational versions of the board. This is max. This is with everything on board. One connector may not be there and a bunch of components, and the other connector might not be there and a bunch of components, right? So you get these 2 variants. And essentially, when I made the prototype for this with a soldering iron, it took me 4 hours to build the unit. I then built the unit using a release candidate board, a test article board. And I used a stencil. I actually made a jig for the stencil. I'll show you the jig. So here's the jig. The board goes into the jig like so. Obviously, it's not going to fit now because there's a bunch of components on here. But let me just place that in. And then the top of the jig comes on, and I paste the board. Pop that off, and the solder paste is applied nice and evenly. And then I hand placed each of the components. There's battery charging on here. There's battery protection. There's the main microcontroller, and there's output and input options for this board. Now, what the time? So bearing in mind, I've got a bin full of components that I'm sifting through, and I'm placing the components by hand with a set of tweezers, and then putting them in my reflow oven to solder it using the reflow oven. See that robot project, says Road Rally Race. There's a gap in the board too. Absolutely, iFrog. Absolutely. There's a good reason for that. It is a requirement. Anyway, so I reflow them. So so pasting the board, putting the components on in a disorganized way, it took me 2 hours to put one board together. I have 100 units to make. 2 hours per board is not going to cut it. So I printed out a bunch of plastic containers. I wrote all the component names on them. and I batched out and had them laid out in front of me, all of the components that I needed. What I also did was I wrote an assembly manual. And the assembly manual contains a map of all of these components, right? So we've got a copy of my board, and each page is a different group of components. So the first page is like all my transistory type components, so MOSFETs and transistors, and I've used a highlighter pen to say where the component goes. I then fold over, I've got my fuses, fold over again, we've got now resistors. So this page shows all of the resistors on the board from 1 ohm all the way to 100 kiloohms. Then we go to capacitors, and we work through each of the component groups until such time as we get to the final components, the largest of the components, which is the ICs. So in that, I was able to reduce the build time from 2 hours to 23 minutes, which is a significant saving. Now, as I say, I'm making 100 of these units, and these units are being made in a panel. And this is one of the panels that we've got to assemble. So this panel consists of 14 boards and represents 23 minutes per board, which equates to 5.5 hours worth of work. So we're going to use the Lumen to put these things together. So I'm not doing the money side of things, but I heard the quote for the number of units we needed manufactured wasn't the done thing. It wasn't workable. Not right now. It might be a bit more workable a bit further on down the line. And there's potential that there are bugs in this in these boards. So, you know, if I need to make adjustments, if I need to put an air wire in here or there, which I definitely hope I don't have to, the test article that I made worked fine. Right? The test article I've made works fine. So that should not be an issue. It should be a fire and forget. But, like I say, this is the first round. Once we get the confidence on that we've got, one, the hardware tight. The hardware needs to be tight and is without error. And the second thing is we need the volume. Once we got those things, we can pretty much, you know, send these out for manufacture. So that's the story of putting these things together. I've got a bunch of feeders which I've made. One of them, I've got 2 different variants. I've got, in fact, I'm gonna have more than 2. This feeder is for thin tape, as you can see, and it takes like a very thin tape film of components. And essentially what this does, the reel sits over here, it feeds in this way, and it gets drawn through the feeder. And the pick and place machine will put the nozzle into the perforation and drag the filament forward. And in doing so, it causes this gear mechanism to actuate. And I can demonstrate that by just dragging that backwards and forwards. You can see the components sliding in and out of the feeder itself. And the purpose of this gear mechanism is you take the film, the clear film, off the top of the components, exposing them so the pick and place machine can grab them. And the tape gets fed into this gear mechanism. And it retracts, it pulls the film off the top of these components. So you always have this window here which has components available for the pick and place machine to grab. So I've got this variant, I've got a paper tape variant for 0603 components. That's the size that we're going, 0603. I'm potentially going to make some variants for the diodes that we're using, and possibly a bunch of other components. I mean, one of the components that we got is the brains of the operation, the ESP32. And we've actually got a reel of ESP32s. And the reel is massive. Let me show you this bad boy. This is quite a sight to behold. So there is the reel of ESP32s, right? Ideally, I want this on the machine. So I'm potentially going to make a custom feeder for this this reel set, and it'll be dedicated for ESP32s. But yeah, I've got a lot of feeders, and I've got a bunch more. Right? I've just tossed them all on the floor here. So yeah, I've got a lot of feeders. We're probably going to be looking at around about 20 plus feeders on the bed. So we'll have to see how that works out. Right, okay. Isn't that illegal? These are feeder. No. Anyway, moving right along. Let's turn this on. Let's see if we have now got a course calibrated XY motion system. So we'll power this up. Have I got prawn to face on here? I don't. I'm going to have to get prawn to face on here. Get print run on. So I can use a graphical clicky that we can drive this rather than raw G code. Okay, so we're powered back up. We're going to do a G28. G28. So we're homing XYZ. I might need to increase the speed of the homing feed rate because that's a little bit... Okay, so now let's get G0, Z0. Let's get that to its 0 point. Okay, so G0, X, 300, feed rate of 12,000, and go. All right, so that is good. I don't. So G0, X0. Nice. All right, let's. I'm going to set this back to 5,000. G0, X300, and then we'll go to the maximum at a lower feed rate because I don't want to. I don't want to slam into the side of the machine. G0, X, 437. We're going to limits, right? 437, feed rate 5,000. Oh, we didn't crash. No, that's good. We didn't crash, and we are butted up right up against the end stop. So that is perfect. G0, X0. Let's make sure we come back to our home position. We do. Excellent. So the X-axis is bang on. It's right on point. So now we need to see whether or not our Y-axis is on point. So let's go G0. Y, what was our Y? It was 485. G0, Y, 485. We'll keep the feed rate at 5,000. Let's keep an ear out to see if we crash. We'll hear it in a like a grinding sound. There's a definite thud. There is definitely a thud as it reaches its designated spot, but it's not is not the sound that you get when you hit something and you go a little bit further than you should. So if we go G0, Y0, do we come back to home? We do. Perfect. So X and Y appears to be calibrated. I'm going to send it full bore. G0, Y, 484. I'm gonna pull short a millimeter. And we're gonna go full speed. Let's see what happens. This might be a really bad idea. This might be a really, really bad idea. But let's see what happens. 484 and feed rate of 12,000 millimeters per minute. Okay, in 3, 2, 1. Oh, and we lost steps. We lost steps. So that is the fact that we lost steps is feeding into my mindset that the stepper driver is getting too hot. It's not too bad. Touching it by hand it's not, you know, it's not uncomfortable to hold my hand there. All right, well, let's go G0 Y 484. Did I set it to 12,000? Feed rate 12,000. Yeah, that's losing power. G28. So that's losing power on, and it's skipping steps at that point. Let's go down to 10,000. G0 Y 484. Feed rate of 10,000. Nice. Okay, let's go to its maximum. Let's see if we can hear that thud. 485. Yeah, it's a distinctive, like, thunk. It's not a whack, like it's hitting it. It's almost that it's getting to its limits and it is stopping where it needs to. So that is really good. I'm driving a machine with text commands. It's like, it's the craziest thing ever. In fact, let me show you what I'm typing, and then that would like make a little bit more sense, right? So if I go here and we do scene input. Where are you? Trying to find the scene I want to add in here. Give me one moment, please. There it is. Okay, so we'll put that over the top like that. We're going to crop this down. Okay, and we'll pop this up the top. So what I'm doing, I'm typing in here. So G0 X. So G0 is a movement command, an absolute coordinate command, not relative. So if I do a relative, I can say like move 10, move 10, move 10, and total it's move 30. Absolute is go to these coordinates on the bed. What speed are they meant to run at? I don't really know Road Rally Race because ultimately it's a 24-volt system. It's different setup. So we're using a Ramps 1.4 board as a little bit of a fudge, really. We're kind of winging it a little bit with hardware, which should we really be doing this? 12k millimeters per minute, NEMA 17. Only no wonder your size and axis heaviness is so much with all the MGN 12 slider rails. Yeah, true, but we do have two NEMA 17s on the y-axis. Right, so let's go 400, and we'll say the Y command, go 400 by 400. Right, the feed rate is already set, and we hit the return key, and off she goes. So yeah, we're sending commands on a text editor per se to do this, right? So it's a little bit like Mr. Bean sitting on top of his Mini in an armchair, driving his car with a mop and a piece of string, right? You want it to be faster than mine? Well, yeah, then buy the official one, because it'll probably will be faster than mine. So I've got a bit of droop I need to fix on my I got a bit of droop I need to fix on my drag chain. Yeah, less said about that the better. I've just noticed that my drag chain is loose because I slackened it off the other day. So let's tighten that back up and make sure that that isn't the reason that we're getting the droop. If we may need to put some sort of support mechanism in place, because what we don't want is to pinch the drag chain between the axis and the stop on the other end. So that has stiffened things up a little bit, which is good, but it's still a bit droopy. So I need to find a means to support it. In fact, what I am noticing, I just realized that my most of the droop is caused by the flex in my custom drag chain bracket. So my plan is to remake this anyway. I think what I'm going to do is add I'm not quite sure the technical term, but put a brace in here. I was going to say some sort of webbing, but no, it's not that. I'll put like a triangular brace here, and I will put a knockout here with a pin that goes down into the X-axis 2020 rail, so that I can screw this down into the rail, and it will make this pretty much solid. And I'll put the brace, potentially put the brace the other side here, so it can't bend, and it shouldn't flex. When we put a M5 bolt through there and bolt it down, that should sort out all of the droop issues, because I can see as I press there, that's where that problem is, right? So this is me prototyping on the fly, trying to make things that are non-standard to the machine work. So that kind of has tripped me up in this regard, but it's a process, right? We're gonna get this working. But so what's left to do on the motion system? Reprint this drag chain and swap that out. That's a done deal, right? That's happening tomorrow. We need to calibrate the z-axes, and we need to figure out how we can get the z-axis to return to its center point. The 0 point is the midpoint in the belt, so that when we go plus 20, one of them goes like that. When we go negative 20, one goes like that, and we have full control over nozzles 1 and 2. Once we've done that, I guess I need to install the NEMA 11s. I'll do a quick show and tell of the NEMA 11s. So the NEMA 11s are the small motors that have a hollow shaft, and they have a pneumatic fitting on the top. That's where our vacuum line goes, and that then pulls a vacuum through this nozzle that allows us to pick up our components. So these drop into here like so, right? And this cable needs to be routed through the jag chain and back down to the controller. We're going to hook these motors up to the extruder stepper drivers, and that's how we're going to control the rotation. So we're going to have to figure out how to calibrate these as well so that we get the correct steps per millimeter so we can rotate the components and orientate them for placement properly. So it's a gusset, right? Okay. So we've got 2 of those to go in. We've got a vac line to feed in. We've got the vac pumps and the solenoids to wire into the ramps board and figure out how we're going to drive them. We're probably going to use the hot end and heat bed MOSFETs to drive the pumps. But then I've got a relay board that I'll be using for... It's a 4-channel relay board, which I'll program some auxiliary ports to control the solenoids to release the vacuum and also to power on the LEDs. Now, the LumenPnP has a... let me show you on the bench. So on the bench, we have the cameras. So the camera has this light housing, and it has WS2812 LEDs on a custom PCB, and then there's a power connector and data line here, 3 wires to run the LEDs, and then it uses the NeoPixel library to turn these on and off. And the same goes for the camera that looks up. There's this shroud that sits on top, and the same deal, right? The camera, there's an illumination, so the camera can find the component, it can find the fiducials and orientate itself. So I don't have that board. So and I don't know whether I could make it work with the ramps hardware anyway. So in the true tradition of hacking this, I'm going to make a standard white LED array that goes in here that we're just going to drive off a relay to turn it on and off. That should be sufficient for our use case and should illuminate the nozzle and the boards well enough to find the relevant reference points. We probably will upgrade to the WS2812s and when we progress to full-blown Lumen hardware, which we do plan to do. It's just that the time frame, I just got to use what's lying around me in order to get the Lumen up and running right now, because we're on such a tight deadline, and the lead times for these components anyway, you know, there's a bit of a wait time for them. So it's not insurmountable, but it's not compatible with our project timelines. The critical path says no. So that's where we're at with the Lumen. Thank you so much for hanging out. If you like the content that I'm making, walking you through the process of building the LumenPnP, if you're watching on YouTube, please give this video a thumbs up. It does so much to help distribution of a video. If you're not already subscribed, if you're watching me for the first time, consider hitting that subscribe button. I stream most Mondays, and I make content around bootstrapping, making projects from scratch, and learning along the way. If you are watching on Twitch, hit that follow button. And thank you so much for hanging out tonight and chatting. Thanks, CE Waffles. Thanks, Guinness. Yeah, hit the thumbs up, peeps. You got it. We want to raid. Okay, well, we're streaming on Twitch and YouTube tonight, so we're not going to raid tonight. So for those of you on YouTube, raiding is an activity that you do where you take your audience to another content creator. It's seen as a very positive thing to do. But because we're multi-streaming, I'm not going to do that tonight. But anyway, thank you so much. I'm going to work hard to get this machine done. Hopefully by the weekend, we have a machine that is close to, if not, in an operational state. That's my stretch target. Wish me luck. Until then, have fun, be safe. I will catch you in the next one. Bye for now.